In this example, we're given the graph of a polynomial function, and our job is to find an equation that would produce such a graph. I'm going to start by just producing a bunch of linear factors in my equation to show you how this may play out. So for example, notice that my graph crosses at x equals 2. It's important to look at just the x-intercepts at this point. Since the graph crosses at x equals positive 2, I'm going to write a linear factor x minus 2, and I'm going to do the same thing and make a linear factor for x minus 4. Notice I changed the sign on the x-intercepts from positive 2 and positive 4, and in the equation I made it a minus 2 and a minus 4, and that had the desired effect of getting these two x-intercepts. If you want a quick explanation why that works, is look at what an x-intercept is. It's a point so that when someone were to replace x with 2, they'd get an output of 0. By changing the sign, exactly that would happen. If you were to replace x with 2 here, you would get 2 minus 2 or 0. It wouldn't matter the value of this factor at x equals 2. It would be some number. In fact, it would be negative 2, but that's irrelevant because it doesn't matter what this factor comes out to be. It'll be some number because this factor would be 0, and 0 times any number is 0. So replacing x with 2, this becomes 0. 0 times anything is 0, making the whole product 0, and that is my output. And then the same logic would work with x equals 4. If someone were to replace x equals 4 in this factor, they would get 0. Replacing this with x equals 4, you'd have 2. But again, this is irrelevant that it's a 2, but it's nice to point that out. This would be 2, this would be 0. So plugging in x equals 4 gives you 2 times 0, or 0 has the same desired effect of having that x-intercept. Now you could repeat the logic with the other factors, x-intercepts. If x is negative 2 is a desired x-intercept, then you could change the sign and produce a factor of, say, x plus 2, and then likewise x plus 4. And the same logic applies when you change the signs. It produces the effect that when someone replaces that x value into the equation, it makes one of the factors 0, which makes the whole product 0. My point here is that that only gives you the x-intercepts that you desire. It does not give you the rest of the graph. So for example, look at the fact that my graph goes as low as about negative 2 and only as high as 4, whereas my graph goes really low and really high. So far I can't even see it. So this is one way to explain how to get the y value smaller, and I'm going to do that via multiplication. In mathematics, if you think of this entire thing as my output when someone plugs in an x value, think of all of that as representing my y values of points on my graph. I want to make them smaller via multiplication. So to do that in math, to make a number smaller via multiplication, you have to multiply by a number smaller than 1. So for example, suppose I put in say a 0.1. Watch what happens to my graph. I still have the same x-intercepts. Those don't change. In fact, if I was to replace x with 2 again, notice this factor would be 0, and 0 times anything would be 0. Since I'm using multiplication here, it doesn't matter that I multiplied by 0.1, because this would be 0 at x equals 2, and 0 times any number is still 0. And what I want to do, though, is even shrink the graph even more. This is called a vertical shrink or compression, because notice that my graph still goes too low and too high. I want it only to go as low as negative 2 and as high as 4. So you could keep guessing, and I'm going to guess 0.06, and notice that I'm almost there. It goes to 3.84 and as low as negative 2.16, but still isn't exact. And there's a different video to show the exact number. That's the whole algebra of it. I'm not going to accomplish that in this video because I don't need to. But I just wanted to show you that the algebra plays out. If you watch the other videos, that they put an A here to represent that vertical scaling. And I have a slider here that allows A to take on different values, and I just wanted to point out that notice no matter what A value I put, the x-intercepts will stay the same, but all of the other points in the graph will be changed. So I'm going to let A be 1 to start with. If A was 1, it would be as if it wasn't there at all, right? Because multiplying by 1 doesn't change anything. So right now this is the original graph where it was too big, so to speak, and as A gets smaller, I shrink it down until I get the desired result. You know, how small do you want it? And I want it small enough so that it goes as high as 4 and as low as negative 2, and I didn't quite get there because of my step size on A here, but you get the idea that multiplication here on the outside accomplishes just that. Now you can watch the other videos and see how the rest of the problem plays out in terms of plugging numbers and actually getting the A value.